Okay. Today we continue our studies of stochastic derivative in multidimensional case. Before we go to multidimensional case, let us recall what we did last time. So we have standard normal variable and discussed the series expansion of square integrate random variable which are measured with respect to psi. It occurs that such random variable can be uniquely expanded as a series of Hermite polynomials from psi also, we know that all polynomials are dense in this space. So we have such expansion, and we have a very good property of Hermite polynomial, which can be easily derived from its definition. That derivative of the Hermite polynomial is equal to n multiplied with Hermite polynomial of smallest degree. So one can try to define stochastic derivative, simply derivative of the random variable alpha as a series n h n minus 1 from psi. Of course, this series does not converge for arbitrary random variables, which is square integrate. But when it is converged, we say that alpha has stochastic derivative, simple derivative, equal to this sum. The set of all such random variables which has stochastic derivative, we define, we denote it by W1. Notation is similar to notation of the Sobolev space in theory of partial differential equation, and it is not. And the reason is that this exactly Sobolev space, because we proved last time that D is a closed operator, and this space of differential random variables can be described as follows. We can consider alpha as a function of psi where f belongs C on R. So this is a space of continuously differentiable functions with bounded, which are bounded together with their derivative. Then d alpha, as we know, is equal f prime of psi. And moreover, one can check that for all beta which belongs to W1, one can find a sequence f n psi such that f n psi converge to beta and f n prime psi converge to d beta when n tends to infinity in it is not hard having this definition to produce the condition for random variable to have stochastic derivative in terms of its coefficients. So let's write the following remark. Let's write the following remark that alpha belongs to W1. It is equivalent that sum of n equals 0 to infinity n factorial n squared is less than infinity. You see, this additional n comes from here because when we calculate the quadratic, the expectation of the square of d alpha, we get here n minus 1 factorial, as we said today, and an square and n square. So one n goes here and we get n factorial and another n remains to be here. So you can see from this remark that you can very easily find a lot of examples of random variables which has no stochastic derivative, at least because of for usual square degree random variable, we have such series without this n. So it's evident that you can produce such a n that series without n converge, but with n does not converge. So we see that stochastic derivative inherits a lot of properties of usual derivative. And moreover, chain rule also is valid for stochastic derivative. And if we have some good function f, for example, f belongs C1, again with bounded derivative, and we have alpha which belongs to d, which belongs to W1, then one can check that there exists df of alpha, which is equal f prime of alpha multiplied by d alpha. This can be usually achieved by approximation of alpha variables which have a smooth representation with respect to psi, as we mentioned today. And please check this as an exercise. So we see that in one-dimensional case, a stochastic derivative is more or less the same as usual derivative. Now let's consider some interesting new operator which we can already introduce here. Let me recall you that one can consider stochastic derivative as an unbounded linear operator acting in the space of square integrate random variables. So we have A2 sigma psi, and we have here W1, and the operator is following. We have alpha from here, it maps in d alpha, and from this point of view, one can say that d is unbounded by the way, but closed linear operator in A2 sigma psi. Let us note that its domain of definition, W1, is dense in A2 sigma xi. It is trivial because W1 contains all polynomials. So we know that domain of definition of stochastic derivative W1 is dense in A2 sigma xi. So at least formally one can try to define a joint operator. Let us look for a joint operator. I will denote by E capital. In the future, we will understand why such a state later. The adjoint operator. Let me recall the definition. We will say that random variable beta belongs to domain of D of E if for all alpha which belongs to W1, the product expectation of beta multiplied D alpha can be expressed as expectation of some random variable gamma multiplied on alpha. And in this case, maybe it's better to say here, if there exists that gamma, is that in this case, we will say that gamma is exactly E of beta. Of course, it can happen that there are no such gamma, but if it exists, it is unique. And uniqueness follows from the fact that W1 is dense in A2. Because for dense set, we will have the same expectations. It means that gamma is unique. So we have such a definition of the adjoint operator. And since it is rather formal and just formally taken from functional analysis, let us check what does it mean in terms of the coefficients of expansion of random values beta, alpha, and gamma in polynomials. So for a moment, I will suppose that alpha is the sum from n equal 0 to infinity an hn psi. Beta is sum from n equals 0 to infinity bn hn psi, and gamma is the sum from n equals 0 to infinity cn hn psi. Then using this relation, one can check that expectation of beta multiplied d alpha is equal to so the sum of n equals 0 n factorial bn multiply n plus 1, and here is an plus 1. Yes. From other side, one can check that expectation of gamma alpha is equal to this sum from n equals 0 to infinity. Here is n factorial a n c. Comparing to this equality, we remember that we must have the equality there. We understand the Cn must be equal so Cn is equal to B N, not exactly, Bn minus 1. Yeah, am I right? Let us check again. If we put it inside, if we define in such way, then here I will write instead of Cn Bn minus 1, or we just change here index of summation. Yes, so we can put here n equal to 1. Then an, yes. Then we get there from n equal to 1.
Maybe we have to divide n factorial or something like that. By n.
Here is n minus 1, and here we will have n factorial. Exactly. So we have such a relationship that in this case we have such equality for defining our random variable gamma. Since then, we have that E of beta is equal to sum from n equals 0 to infinity. By the way, maybe better write 1 to infinity. Here is b n minus 1 h n psi. Okay. From this, one can see interesting properties of this E. First of all, it occurs that it is densely defined. Why? Because trivial, its domain of definition contains all polynomials. For finite sum, this series will correct. For finite sum, it is not defined. This is one remark. Another one is the form. That expectation of this adjoint operator is always equal to 0, because we have no 0 term here. More or less, if we take expectation of E beta squared now, it will be equal to the sum from n equal 1 to infinity n factorial b n minus 1 square, and it is exactly the same that sum from n equals 0 to infinity n factorial b n square. Yes. I just change n minus n plus 1 factorial. Excuse me. N plus 1 factorial. Okay. Bn square. And let me recall. It looks very similar, like definition, like the norm of stochastic derivative. Only here is n plus 1 multiply n factorial instead of I can continue. So it looks like expectation of beta squared plus expectation of d beta, which must exist. So in this case, one can see that we have the following conclusions, namely domain of E coincide with W1 and we even have two such relationships for first and second moment. It is just algebraic way of thinking. So let us recall that we already defined so-called weak product for some random values. Let me recall you what does it mean. Let me recall you what is weak product. If I have two random values, alpha 1 is equal sum from n equals 0 to infinity h1 and hn psi, and the same alpha 2 sum for n equals 0 to infinity an2 hn psi. Then the weak product alpha 1 alpha 2, if it exists, of course, was equal to n to sum from n0 to infinity, and here is sum from k equal 0 to n h k1 h n minus k2 h n h n psi. Okay, so it looks like Cauchy product of two power series, but instead of powers we use Hermite polynomials. Yeah? And maybe it's good to have here brackets. And of course, it is not well defined for arbitrary square integrate random variables, but we have seen, for example, as the following expressions that psi multiply psi n times is exactly a polynomial of h and psi. Why this expression was introduced? Because the Fourier-Wiener transform reacts in very simple and nice way on this product. So we keep in mind that maybe it is like a convolution. Yeah? And now let's consider special example of this weak product, which occurs to be related to our considerations today. Consider the following partial case. Let us have the random variable beta, which belongs to W1, which already, as we have seen, this is only for one-dimensional case. because in multi-dimensional case, we will see this domain of definition of a joint operator is larger than this one. But in one-dimensional case, which we are studying, we have equality here. So consider random variable beta from there. Consider its expansion. Here is the series from 0 to infinity bn h psi, and let us try to look for the product with psi. What it can be? Let me recall you that psi is equal h1 of psi. Its expansion has only one summand. So due to this, we have the following. This is equal sum from 0 to infinity. B n h n plus 1. Yes. This follows from the definition of weak product, which I already presented today, and you recognize that this is exactly E of beta. So in our case, we have the following. A joint operator acting on beta is just weak product with this psi. Here is a very nice relation, which we will continue to study in multi-dimensional and infinity-dimensional case. Moreover, let us now check what is this E multiplication on weak product with psi in terms of smooth function. Because we remember that here in this space, we have a special good set, which consists of smooth functions from our random variable psi. And we already know that for this smooth function, stochastic derivative is nothing else than a usual derivative. Yeah. So let's check what is this for such a good random variable. So I will take just a random variable beta, which can be represented as follows, where f is from this space CV1R, C1B. So as I said, this is a set of continuously differentiable functions which are bounded together with their derivatives. And now let us try to check what is this. Yeah. I will use the definition. And in order to use it, I will take alpha, just a polynomial from psi, p of psi. It is enough. Maybe you understand that this is enough, because again, polynomials are already dense in the space of square integrable functionals from psi. To find this answer, it is enough to check the definition of a joint operator using this alpha as a test function. So what we will have? We will have the following expectation of E from beta multiply alpha must be equal to expectation of beta multiply on d alpha. So I will start with this right-hand side, yes, and will transform it in order to understand what is this. Let us do this. Let us consider E beta d alpha, and due to our representation, it's equal to the integral with respect to r. Here is f of x because of this one. Then p prime usual derivative, because we remember that stochastic derivative for good functionals from psi is just derivative of this functionals. P of x, and here is 1 over square root of pi. Here is e minus e square u dx. This is standard density. Now, what I want to get here alpha. So I want to get rid of this one. Yeah. How I can do this? Just integrating by parts. Yeah. So I will continue. To do this integration, let me recall you. F is bounded together with this derivative. This is polynomial, and this is a rapidly decreasing function. So it is a good case for us because when we will get the summands in integrating by parts formula, we will have no this summands related to minus and plus infinity. We will have 0. So what we will have exactly? Let us continue calculations. We will have the following. It will be equal to minus integral of here is p of x is now without derivatives, good sign, and here is let us write it precisely, f of x multiply this density e minus x squared prime dx. Now let's use the formula for the calculus, and we will finally get the answer. It's equal to minus integral with respect to r p of x. Here is f prime of x minus x multiply of x, and here is 1 square root of 2 pi e minus x squared dx. Yeah. So now we can just do final step. I will put this minus inside of the brackets. Let's allow me to do this using this eraser. So we will get finally x multiply f minus f prime. So finally we have such an expression, and it must coincide, as we discussed, with the expectation of our alpha, and here's T of beta. And from here, we understand that because of alpha is represented by this polynomial, and polynomials are arbitrary, then this is a representation of our beta. Finally, we get the following nice formula, which represent for us a joint operator to stochastic derivative. So E star beta equal E beta equal beta product with psi is equal to now psi beta minus d beta. Yeah. So now we have such a good representation, and we understand that a joint operator to stochastic derivative can be obtained from the integration by part formula with respect to our Gaussian measure. and it will hold also in infinite-dimensional case, as we will see. So we see that this operator, despite of its formal definition, like conjugated operator to some good linear operator in L2 space, occurs to be again differential operator, occurs to be related to integration by path formula with respect to Gaussian measure. This is additional term. In case of Lebesgue measure, we have exactly such formula. And occurs to be related to the weak product with the initial Gaussian random variable. Now I will give you a surprise because not today, maybe next time, we will see that this operator occurs to be operator of stochastic integration with respect to Wiener process in Ito theory. You see? So we have such a very rich object, and to continue its study and make it much more interesting, let us jump to multidimensional case. So now we start to study the case when we have the space RD, and we have here psi, which is equal psi1, psi d. It is standard Gaussian random vector. Yeah? Is standard Gaussian random vector. So it consists of independent starter normal variables. It has zero mean and identity covariance matrix. What is our plan? We will discuss expansion for alpha which belongs to L2 sigma psi. Then we will discuss stochastic derivative, d, and the last one is E equal d star. This is our plan, and this is just blocks of our consideration, because inside we can have, of course, discussion what is stochastic exponent, what is weak product, and all related things. Yeah. Let's start from the first step, the expansion for alpha, which is square integrate, and which is measured with respect to psi. What we will we already know, and maybe it is not necessary to repeat it again, that polynomial from this vector are dense there. It is not very hard to prove, and I ask you to do this, to repeat the proof as an exercise. So we already know that polynomials, so such set like P of psi, where P is a polynomial, they are dense in L2 sigma xi. And then one can try to find the expansion with respect to orthogonal polynomials, but in multidimensional case, for any elements from there. In order to have this expansion, let us introduce some notations. Why I need new notation? Because when we discuss one-dimensional case and organized orthogonal polynomials, if we fix the degree n, there exists only one polynomial from this orthogonal sequence related to this n. If we agree, for example, that it is normalized, or if we agree, for example, that its main coefficient is equal to 1, as it was happened with our Hermite polynomials. But in multidimensional case, the degree of polynomial does not fix their main component. Yes, for example, this is a polynomial of degree 2. This also is a polynomial of degree 2, and so on. Yeah. So in this case, we have a lot polynomials of the fixed degree. Yeah? And maybe we will have a lot of orthogonal polynomials of the same degree. So let us produce some good notations. Let us consider Pn. It is a set P of psi such that degree of P is less or equal to it is a company of all polynomials which have a degree which does not exceed n. Now let us consider this Pn as a subspace. It is finite dimensional, of course, subspaces of L2. We will have such inclusions. P0 is evidently included in P1, and so on, and Pn, and so on. Also, what we have that the union P, this is a union of this Pn, is dense in L2. So now I can do factorization procedure, but I will do this procedure not with the fixed functions or fixed elements of Hilbert space, but with the subspaces. This is very familiar procedure from the functional analysis, and I will introduce the following notation. Let H0 will be equal to P0, and H1 is the orthogonal complement of P0 in P1. So it will be equal P1 minus P0. Let me recall you that this is minus in the circle, which means orthogonal difference, yeah? Orthogonal complement. And so on. So we will have Hn plus 1 is equal to Pn plus 1 minus Pn. In such a way, we get a family of orthogonal subspaces, orthogonal finite dimensional subspaces now of our space A2. And the corollary of the fact that all polynomials are dense in our L2 is the following. that such a orthogonal sum this from n equals 0 to infinity hn is equal exactly to sigma psi. What does it mean, this equality? It means that if I organize projections, En does not please do not forget about this index, because without index it will be related to our adjoint operator to stochastic derivative. So En is a projection onto Hn. Of course, we are working in Hilbert space, so I mean orthogonal projection. Projection in this Hilbert space onto Hn. Then, for all alpha which belongs to our L2 sigma psi, we have the unique representation as the sum from n equal 0 to infinity En of alpha. Okay. So what is En now? Of course, En is a polynomial of degree n. So we have already expansions of any functional which is of psi, which is square integrate, as a series of orthogonal polynomials. Yeah. And formally we did at least small step in the right direction. Why I am saying that small step? Because it is desirable to understand the structure of the summas. What is this? How one can present this summa? And let me say to you that at least we can produce at least one answer on this question. I'm claiming that we know one answer on this question. Let's do it. To understand why I'm saying that one answer we have, let us recall the space with which we are working. This is a space of such function. Let me recall that psi has independent normal coordinates which are standard normal vectors. So one can say that this is a tensor product of k equal 1 to p. Here is A2 sigma psi k. Why? Because again, what is this? This is a closure in L2 sense of all polynomials. All products, all linear combinations of products of this one. What is this? By the definition of tensor product, this is a closure of linear combinations of products of these functions. But polynomials are dense in every such space. So this is a closure of products of polynomials of psi k. It is exactly the same. Due to this representation and properties of tensor product, one can say that now if I have element from here, then it must be uniquely represented as a following series. And here I'm doing the following. I have a tensor product of Hilbert space. In every Hilbert space, I have such a complete orthogonal system. HK from psi, excuse me, HN from psi k, n is greater or equal than 0. So what will be the orthogonal system in the tensor product? Of course, it is a system consistent of such product. Hn1 psi n psi 1, Hn d psi d. This is an element of new orthogonal system. It is trivial to check this. Then alpha can be uniquely expanded with respect to this system, and I will have the following: in d equals 0 to infinity, sum a and 1 and d, and here is h and 1 psi 1 and so on, h and d psi d. We have the orthogonal expansion of alpha with respect to polynomials of psi. Now, what is remaining to do? I just have to collect summands there related to same degree. Yes. So finally, I will have the following expression. It's equal to sum from n0 to infinity, sum here is n plus n1 plus and so on plus d equal to n, a n1 and d. Here is h n1 psi n h and d psi. Okay. So here is exactly E n of alpha. So we just can have the answer. What is the projection of E of alpha onto the space H n in our case? By the way, you see here again the notation H, but it is also a historically recognized notation. So we will use it despite it coincide with notation for polynomials. I think that we will have a lot of misunderstandings. So we have such answer. But of course, this is not satisfactory answer. Why? It is complicated, you see. Of course, we can say that alpha is corresponding to the set of these coefficients. And even we know how to find these coefficients, we just have to take expectation of alpha with this product and divide it into n1 factorial and so on, and d factorial. But it is desired to have a much more simple, description for this polynomial, and the second reason is much more deep, because of course we always want simplicity, but in some case it can be not achieved. But there is another. And the reason is that always when we are working with vectors, matrices, and so on, it is desirable to have the description which is independent of basis. So it is desirable to have a language, not matrices, but operators. And have such statement that can be transformed infinitely dimensional case without relationship with some special choice of basis. This is our next aim, and let us try to do this. Who can help us in this way? Maybe you remember that in a one-dimensional case, there was a very interesting one random variable whose expansion help us to find coefficients for other random variables and who help us to define Ito-Wiener expansion. It was stochastic exponent. So let us try to define stochastic exponent there. Maybe it will help us to understand how to write these elements in such a more simplest way, which does not depend on special choice of basis. Let's do it. So let us consider stochastic exponent in multidimensional. I will define it as follows. I will take a vector lambda, which belongs to Rd, and put to it into correspondence the following random variable. E of lambda, it is an exponent of scalar product lambda xi minus 1/2 of the norm of lambda square. Here I mean Euclidean norm and Euclidean product. In coordinates, it looks like exponent. Here we have sum from k equal 1 to d lambda k psi k minus 1/2. Here is a sum from k equal 1 to d lambda k squared. Why I am writing this stochastic exponent in coordinate form? Because when we have such an expression, it is easy to see the expansion into orthogonal polynomials for this random variable. Because this is just product of one-dimensional stochastic exponent, which are generating function for Hermite polynomials. So it's easily get the orthogonal expansion for this random variable depending on lambda, and it is the product from k equal 1 to d. Here is a sum from n k equals 0 to infinity, and here is lambda k in ak power over nk factorial, and here is hnk from psi. This is what we already know about the one-dimensional stochastic exponent. What is remaining to do? Just do multiplications, yeah? And then we'll get the following. It's equal to the sum from n equals 0 to infinity. Here is another sum, n1 plus nk is equal to n, and here is lambda 1 and nk1 lambda 1 and k1 and 1 multiply lambda d and in nd power divided by n1 factorial and d factorial multiply the product h and d psi 1 h and d psi d. Okay, so one can easily get the orthogonal expansion for our stochastic exponent, and we see how it looks like the nth element of this orthogonal exponent in our case. Now, what is remaining to do, as before, to get some product, to get the expectation and understand how we can write this expectation in a good way. But we will do this next time. Today we just finished our lecture with the series for multi-dimensional stochastic exponent. Thank you for attention. Maybe somebody have questions or comments, please.
I have a question for the chain rule.
Mm-hmm.
Can we do the same with normal Sobolev functions like W1, 2?
So you want to discuss the second derivatives, yeah?
No, wait.
With a normal Sobolev function with respect to Lebesgue measure.
Yes, exactly, but W1, 2, so it should be square integrable. And then
yes,
consider
yes,
f of psi, and then
exactly the same. We can do exactly the same, yeah.
Ah, okay. But so there are no problems occurring. But we need to take a representative, I guess, to get the equality in the chain rule.
You consider smooth function f from the Sobolev function. Like here we have you have Sobolev function phi1, pn. If they are Sobolev and this is good, then the derivative of this is equal to, as usual, sum f prime k and so on.
Okay.
There are no any problem. But if you are interested in, there exists a problem related to expansion of this property on the functions which have no moments, which are not integrated. Of course, you can say, let's say are locally Sobolev. Yes, we have just domain. For example, you have a ball inside of which then okay, everything is. But if you will look for such a set which maybe is not open, but still have the properties that you can define properly derivative, disclosable, and so on, then you will get a very nice characterization of this set. And even in infinitely dimensional case, using our Stein-Uhlenbeck semigroup, we can have a characterization of this set. It occurs, roughly speaking, that the following property, like every point must be not only a point, Lebesgue point of the set, but it the speed of convergence in the Lebesgue approximation in every point must be controlled. So maybe, by the way, maybe Nastya next week will mention this on the seminar.
Okay.
Okay, maybe other questions, please. If there are no any questions, thank you for attention and see you next week.